This is what a team of physicists at the Chinese Academy of Sciences actually built, and how far that device sits from the refrigerator humming in your kitchen. Headlines have called it the invention that replaces refrigerators forever, and the physics underneath is sound, though 3 parts of that claim do not survive a reading of the paper. The most interesting part is where the same team went next, which has almost nothing to do with your kitchen. Vapor compression is the process running inside nearly every cooling device you own. Thomas More patented a machine he called a refrigerator back in 1803, and the technology has been refined for close to 2 centuries since. A point the Chinese team makes in the opening lines of their own study. The scale of it is easy to overlook. According to the International Energy Agency, roughly 1/10 of all electricity consumed on Earth goes to refrigeration, and the energy drawn by cooling equipment is projected to more than triple by 2050. Then there is the gas. R-134a, one of the most common refrigerants, carries a global warming potential of 1,430, which means the United States Environmental Protection Agency rates it as trapping that many times more heat than an equal mass of carbon dioxide over a century. Compressors also take up space, which rules them out for anything genuinely small. The cycle itself is barely changed. A mechanical pump squeezes refrigerant gas until it heats up. The heat sheds through coils on the back of the cabinet. The compressed gas condenses into liquid, and that liquid is then allowed to expand, absorbing heat from inside the box as it does. Every part of that sequence depends on a moving pump and a sealed charge of gas. The alternative physics is not new. Emil Warburg observed in 1881 that iron changes temperature when a magnetic field is applied and then removed, an effect now called the magnetocaloric effect, though some historians argue the credit belongs to Weiss and Picard in 1917 instead. The mechanism is simple enough to state in one breath. A magnetic field forces the atomic spins inside certain metals to line up, which lowers their magnetic disorder, and the material compensates by warming. Pull the field away, the spins scatter again, and the metal draws heat out of whatever surrounds it. No gas is involved, and nothing wears out. G.V. Brown built the first room temperature magnetic refrigerator in 1976 using gadolinium, a rare earth metal, reaching a temperature span of 47 Kelvin with a 7 Tesla field. Barclay and Steyert improved the approach in 1982. Haier even demonstrated a solid-state wine cooler at CES in 2016. 50 years after Brown, no magnetic refrigerator sits in an ordinary kitchen. The obstacle was never the magnets. Every serious design pumped a fluid past the magnetic metal to ferry heat away, and that fluid brought dead volume, pressure losses, and uneven temperatures, all of which waste cooling. Fluid also moves slowly, which caps how fast the machine can cycle. Most published prototypes run below 1 Hz, meaning fewer than 1 complete cycle per second, and the best experimental results in the field sat around 29 Kelvin at 4 Hz. A Danish rotary prototype managed 25.4 Kelvin at 2 Hz. A Spanish reciprocating design reached 3.5 Kelvin. An American machine using lanthanum iron silicon alloys hit 18 Kelvin at 4 Hz. Decades of engineering, and the number stayed stubbornly modest. Yuan Lin, Jing Wang, Wei Dai, Kai-Ming Chao, Hobo Zhou, Tongyun Zhao, Fengxia Hu, and Baogen Shen published their answer in the journal The Innovation on May 22, 2024. Their design, called a hybrid magnetic regenerator, stacks 2 counter-rotating layers, one made of gadolinium and one of copper, and lets them touch directly. Heat crosses solid to solid, and the fluid disappears entirely. Simulated at 10 Hz, the device reached a 26 Kelvin temperature span, a cooling power of 8.3 kilowatts per kilogram, and an ideal efficiency of 54.2% against the Carnot limit. Drop to 1 Hz and that efficiency climbs to 73.1%, roughly 10 times what comparable fluid-based rotary prototypes have measured. The authors put one figure on what that would mean in practice. At a 10 Kelvin span running at 10 Hz, 500 grams of gadolinium would deliver more than 2.5 kilowatts of cooling, which they compare to the cooling load of a 50 square meter building. Swapping in a lanthanum iron silicon alloy pushed cooling power higher still, to 9.8 kilowatts per kilogram, about 18% above gadolinium, though with a smaller temperature span. Here's the part the headlines skip. Those numbers come out of finite element simulation run in COMSOL multiphysics, using experimentally measured material properties as the inputs. The paper describes the device as conceptual in its own title. The physical test consisted of 2 gadolinium slices measuring 3 by 10 by 1 millimeters and 3 copper slices, and it produced a temperature difference of 4.6 Kelvin over tens of seconds. The full simulated machine has an outer radius of 10 millimeters and a working core about 0.3 of a millimeter thick. That is not a refrigerator. That is a proof that the geometry might work, and the authors are careful to say so, describing the arrangement as scalable from millimeters up to meters rather than as a finished appliance. 2 obstacles remain unsolved. Friction between the rotating layers generates heat of its own, and the team's proposed fix, a nanometer scale air gap, costs real performance. At 100 nanometers, cooling power falls 13%, and efficiency drops from 54% down to 40%. Cost is the second. Gadolinium is a rare earth element, and China is the dominant global producer, which makes for an odd twist in a story usually framed as a Chinese challenge to Western appliances. Magnetocaloric material and the permanent magnets around it together account for the majority of what such a system costs to build, and that is before anyone attempts mass production. The team did not stop at kitchens, and this is where the story gets genuinely good. On April 20th, 2026, the same group, joined by Victorino Franco, Jiayan Law, Yunjiang Chen, and Zhirong Sun, published a follow-up in the Proceedings of the National Academy of Sciences. This time they built the thing. The target had changed completely. Rather than cooling food, they aimed the hybrid regenerator at microchips, using direct solid-to-solid contact for what they call point-to-point thermal management, meaning cooling delivered to one exact spot rather than a whole compartment. The measured results are the strongest numbers anywhere in the story. Their laboratory demonstrator achieved a heat transfer coefficient of 336 watts per square meter per Kelvin, set against the under 100 that forced air convection from electric fans typically delivers. Area cooling power reached 0.72 watts per square centimeter at a 20 Kelvin difference. The authors write that swapping electric fans for their device could triple microchip performance in machines like laptops and portable medical equipment. Material choice explains much of that. Gadolinium conducts heat at roughly 10 watts per meter per Kelvin, against about 0.2 for the polymer used in competing electrocaloric devices and 1.4 for the ceramic alternative. So far, fewer stacked layers are needed to reach the same result. Fengxia Hu and Baogen Shen appear as inventors on a Chinese patent covering the device. So the honest version runs like this. The underlying physics dates to 1881. The first room temperature magnetic refrigerator was built in 1976, and the 2024 paper that produced all the headlines describes a simulated concept whose only physical test moved 4.6 Kelvin using metal slices smaller than a postage stamp. No announced timeline exists for a magnetic refrigerator in any appliance store. Gadolinium cost and mechanical friction both remain genuinely unsolved, and the same funding that built this came from China's National Key Research and Development Program, rather than from any manufacturer preparing a product line. What did get built 2 years later is a device for cooling computer chips, and by its creator's own measurements, it outperforms every full solid-state caloric device reported for thermal management. Nobody at the Institute of Physics claimed otherwise, and the framing that turned a chip cooler into a dead refrigerator industry happened somewhere between the journal and the thumbnail. The refrigerator in your kitchen is safe for the foreseeable future. The fan inside your laptop is the part that should be worried.